have the closest I come to biology is through, I don't know, maybe the materials genome initiative. Right? So I'm not working in biology, but I'll show you some examples here that one of my postdocs did. A lot of the methods that we've been developing, they have a lot of the mathematical challenges have a lot of overlap with challenges in biology. We saw some in the last couple of days, so they'll come up here too. So I'll just. So basically, I'll talk about two main things. So maybe one main thing, right? So the main thing is model misspecification, right? So when two models are close, by models I understand two probabilistic models, P and Q. So here in this slide, in this first aspect, I'm thinking of two models that maybe they correspond to different parameter regimes, or maybe one includes additional mechanisms than the other model. Maybe it's a more complex model. And I would like to understand questions like uncertainty quantification, sensitivity analysis, and also intimately related questions to sensitivity analysis in statistical mechanics, linear and nonlinear response, also in dynamical systems. Right? So these types of questions here, as we'll see later on, they're important in many fields. So they're important because they allow us to understand what mechanisms are fundamental, what are important. Also, there are some interesting connections recently that I'll come back with later to a lot of work in macroeconomics and finance about model specification. Another aspect of the same thing, but a little bit more concrete, has to do with this concept of surrogate models that people are looking a lot in engineering and applied sciences. So basically, you have a complex model P, stochastic model P, with some probability distribution, and maybe highly complex probability distribution, and then you try to do a best fit, find the best fit model Q from some much simplified family. Typical example of best fit approaches is coarse-graining. In today's talk, right? In today's morning talk, we talked a little bit about coarse-graining, right? So the model was not shown, but coarse-graining was the workhorse there, right? Working behind the scenes. So basically, I have here, you can see this complicated polymer, and I can either describe it at that level of complication, or I can sort of have a reduced model with these blobs that you see over here. You saw some blobs today, right, in the morning's talk, right? And I'd like to know, of course, if this is a good predictive tool, right? If it predicts anything or not. Many examples that coarse-graining fails spectacularly, right? Many examples, even simple problems, right? Similar picture here, right? High-resolution model, low-resolution model, right? Similar issues come up in so this morning in biology, geosciences, atmospheric science. Some of you are working on these problems. Similar questions come up in variational inference. We'll see what that is, right? In case you've not seen it before. In machine learning, where one has to, instead of doing Bayesian statistics straight up, you get rid of the posterior and you approximate with a simplified model, and you do MCMC on that. Right? And of course, lots of work on model selection based on data. A lot of this work also done in biological applications. I have candidate models, and I'm trying to see which one fits best a set of data from some unknown model B. So this is the universe of models that we're supposed to look at. But let me just give you some little specifics about, let's say, sensitivity analysis in UQ. So just to nail down some notation and see what the challenges are, right? So here is sensitivity analysis in UQ for parametric models. So I'm assuming that my model has a parametric form. Is this a parametric form? I won't talk today about non-parametric stuff, but there is work out there on non-parametric stuff in this direction. I won't discuss that. So non-parametric stuff is much closer to the data. Right? So So what I have here is I have an ensemble of models. So P of x given theta, this is my parameter. This is my forward model. Here's a baby example. I'm not interested in the deterministic dynamics today, but I'm giving you here the example for the deterministic dynamics. I have an ODE. That's the probability that it's a Dirac mass, obviously, right? That I am at state x at time t, right? For the parameter theta. But the parameter theta is something that is of major interest to us here. What I'm interested in is in quantities of interest, which could be either observables or statistical estimators. They always take this form for a given theta, right? I'll call them quantities of interest to capture both. The parameter theta could be many. We'll see examples of that. Could be indexing of different models. I'm going to keep it open. And as you see here, P of theta is the probability that I'm getting the particular parameter theta. So in my model, P of theta captures the uncertainty in my knowledge of theta. Right? If I know it, if I really, really know what my parameter regime is, that's a theta zero here. That's a Dirac mass. Right? Right? So the next, so in some sense, so when I write like this, I have an interaction between parametric uncertainty and model, right, and forward model, right? So this could be a complex model. For example, imagine your favorite chaotic ODEs, right? And there is, and one can think of perturbations of parameters in terms of perturbations in this measure over here, P prime of theta. You want to compare this model to that model. Now that has also the parameters in it, right? So I became a little bit more specific than the first couple of pages. This type of formulation also includes classical formulation sensitivity analysis, like Morris indices and so on, and also the classical local sensitivity that we'll talk about in a second. Right? So if I have, if I know my distributions here, if I know this is theta zero, I can perturb it to some new value, theta zero plus epsilon, and see how this thing impacts my let's say quantity of interest or my probability itself, right? So I don't remember what's in the next slide, but
find out in a second.
Yes, I'll find out in a second, right? So I think that maybe it should be something about issues, challenges, right? Maybe. Right? Yes, yes. And also you'll see where my card is, right? It's not in biology, sorry, right? It's materials, right? So although I had a great postdoc, right, who he's in biology, so that helped a lot. So one of the main themes of this talk is scalable UQ. We need to have scalable UQ methods. So what you see here is a catalytic reactor. Giannis is very familiar with that as a chemical engineer.
Okay.
In your previous states, maybe.
Sure.
So here you see the surface of the catalyst, right? It's a highly multi-scale problem. It's coupled with fluid dynamics. So multi-scale issues are key, meaning that long-time integration is key, high dimensionality is key. So I need to be scalable in at least two ways, also in a third way. High dimensions, high T, right? I have to go long times, finite times and long times, right? Also, I cannot be a PDE guy, right? I cannot be a PDE guy. So here's an example, right? An example is here. You see a very hot topic. Let's say catalysis, bimetallic catalyst, multimetallic catalysts. So this is platinum, this is nickel, and you see here the performance of the catalyst. This is the turnover frequency. We saw similar concept in the morning talk, actually. And you see here how it performs for this geometry, this geometry, and this geometry. Now, the densities for this one here, right? If you look at the coverage, they're more or less the same. But the geometry at that tiny little scale matters a lot, right? Performance is very different. So I cannot have a mean field model, I cannot use a PDE model, right? I have to use an actual molecular model, right? So the best thing I can expect is to use a kinetic Monte Carlo. So I'm stuck with stochastic dynamics. And I'm stuck with long times, and I'm stuck with big N, of course, right? Because this is spatially resolved, right? It's not well mixed. What's next? Some other challenge probably. Ah, yes. Yes, complexity, right? So we have a lot of chemistry here, right? Right, like some of the problems in systems biology, right? I have highly complex reaction networks. Okay, they are not biochemical. Well, this one actually is a little bit biochemical reaction network because it's a biomass problem, right? And you see here how the scale of the reaction network as the complexity of the molecules with which I'm dealing with, there is very high complexity in biomass applications. How the complexity of my problem raises. So here you see the network itself, the geometry of the network itself. It's part of the network. And you see here, the more complex the reactants, the bigger the number of reactions and parameters that I have, right? So the number of parameters can go to thousands, right? To thousands, to a billion, maybe almost a billion, right? Same thing with intermediates, right? Intermediate steps, intermediate reactions, right? Very, very high, very huge complexities, right? Huge numbers of parameters. Also here you see that there are some, so this, in such a complex problem, so many intermediates, you might be tempted. You see here, what you see here with these dark lines is that this is the flux in the reaction. These are the most frequent reactions. Right? So you may say, maybe these are not so important. Maybe I can get rid of them or whatever. Or maybe the parameters that are not so important. I can use some nominal values. These are all good questions, right? But the system is very high dimensional, so we have to understand how to handle it. And now, maybe you have not thought about high dimensional systems. Certainly I hadn't, about systems that have a huge number of parameters. Until I started collaborating with people in applied areas, and then I realized that there's a lot of math issues there. And I just to illustrate that, I'm going to give you the textbook example of sensitivity analysis, the one that we don't teach in the math departments in the undergraduate D class, right? We don't teach it, right? All right, so I'm just going to give you an example of the deterministical Ds. Whatever I say here holds for stochastic systems, right? But it's much more amplified, right? Much more amplified. So I have a system of ODEs. Here it is. This is my parameters, right? N dimensions, right? My system is N equations, and I want to do local sensitivity analysis for this system here, right? Now I think that although we don't teach this in undergrad, I think we all know how to do that, right? We just take a derivative, right? Local sensitivity means that I'm going to perturb this theta k, right? Which is one of them, right? So how do we do this? We know very well how to do this. This is a standard trick in math. We take a derivative of this equation, and now we have a coupled system. This guy and the new equation for this guy over here, right? Which is the linearization of this. Right? So how big is this now augmented system? So you see, to do sensitivity analysis, it becomes very taxing, right? If I have k parameters and an n system, so automatically I have an extra k times n additional equations, right? So as soon as I try to do some systems task, things become much more complicated, much more challenging, right? And this is the simplest thing that I should be able to do, right? The simplest systems task, right? Local sensitivity analysis. In reality, I want to do big perturbations. I want to chop off, chunks of my complex model. I want to do much more than this, right? Now, if I am in a stochastic system, inevitably I have to deal with variance, right? High variances might be even a bigger enemy than this, right? Having high variance estimators will be a serious challenge, it is. Rare events, right? I'll talk very little today about rare events. We have some results I'll show you at the end. Maybe if I have time to get there. Oh yes, yes, right. Now the next thing, right? So okay, so all that is fine, right? But there is more, right? There's more. So in a lot of the problems that I'm interested in, the parameters, I can determine them from very complicated, but now fairly streamlined, quantum electronic structure calculation, like DFT, instead of experiments. You may have experiments, fine, right? But this is the simplest thing to do in many of these problems. And it turns out there, right, if you look at this data, so you have data about your parameters, right? So your parameters, you can divide them in two categories, and many times they're highly correlated. So if you have highly correlated parameters, the previous step in this baby example, taking derivatives, is not the right thing to do, right? Because imagine highly correlated, what's the simplest example? That you are on some plane, right? That you have on some hyperplane. So if you're on a hyperplane, your derivatives are not really your own derivatives, right? They are derivatives of this manifold, right? So correlations, hidden correlations could be important. It could change dramatically the performance, right? And predictions. And we have a recent paper on this in Nature Chemistry with this type of observations and examples. So these are some of the issues that we're facing, right? High dimensions, stochasticity, all that, right? So now let's get into business. Let's at least talk a little bit about the framework in which we can sort of address some of these questions, right? How should we think about them? So this is a very classical perspective by now, right? In fields across science and engineering. So we want to use some type of, so since we have this stochastic models, I want to have a way to discriminate between two models. I have the complex guy and the simple guy. I have the perturbed guy and the original guy. I want to be able to differentiate them, right? So here they are. We P is the complex guy, Q is some coarse-grained, simplified, whatever, or it could be some perturbation of my model P. And I want to know if they are close. I'm sorry, if they are close or far away. What is close is some error tolerance, right? So I want to know that, and I have to be able to do this in some metric, right? So I need some type of metric to do this, to play that game, right? In coarse-graining, there are more challenges, right? That you have to you're comparing models which are on different state spaces, right? So you have to do some upscaling, downscaling, right? But I don't think I have time to get into that, although I have enough slides to get there. So what metric, right? So some people say relative entropy, right? The Kullback-Leibler divergence, right? So that's what they say. And this guy here, right? This object that we'll see in a second, right? Measures the loss of information when you replace P with Q. So there are a lot of people who say that, right? And here they are, right? So there are people who do variational inference in machine learning, it's a gigantic community, we'll see more about this. People who do the same stuff in coarse-grained models, materials. People who do sensitivity analysis, you'll see that in much more detail today. People that do predictive skill and various model reduction problems like anti-MIDEF or atmospheric social science problems. And also model selection, right? So I won't talk today about model selection, but it's we said that a little bit at the beginning, right? So this is the tool that is used in model selection. So for example, this information criteria like Bayesian information criteria or KK information criteria are of that type, right? And that's what I use relative entropy. Okay? So why, right? So why relative entropy, right? So why are we using this option? So here, first of all, here it is, right? Here it is. It's log it's P over Q times P dx, right? It has lots of really cool properties, really fundamental and cool properties, right? So I'll just show you. So two of them, right? But there are many more. They have to do with convexity and whatever, right? So it's always bigger or equal to 0, right? You get it's trivial to show. Right, so the properties of the log, the convex properties of the log, and it is 0 if and only if P is equal to Q. Now, this object over there is not a metric, right? So you might be tempted to think that's a metric, but if I flip P and Q, they're not the same. So that's what we call the divergence, right? In this business, it's called divergence. There are also other metrics, right? We'll see them later, right? Total variation and Hellinger and chi-squared, whatever. And the Rayleigh divergence, I sort of have it here in bold because I was planning to say more about this because it's really important when you want to control rare events, but maybe you won't get there. Maybe we can talk offline about this. So is this special, right? Why people are using this? It's convenient, right? Analytical is convenient. We'll see a little bit of that, why it's convenient analytically. We'll see it in action, right? When we do some calculations. It has important computational properties. It has, you can sample from it if you're careful. Also, it has great scaling properties. We'll prove actually that, right? It has great scaling properties, in degrees of freedom, long times, numbers of parameters. All these issues that we saw before, right? So before we saw long times, high dimensional spaces, high number of parameters, right? This scales great, right, for these, right? So we saw that. And also it has some drawbacks. A key drawback is that you need to have absolute continuity, right? You need to have that. So that means that you cannot really, so P and Q cannot be fantastically different, right? More or less, right? If you are in that situation with some other methods which are better, stochastic coupling, yes, everybody having calculus, but the calculus scales horribly in computations. So I won't say anything about this. And also another thing is, of course, this is all great, looks like information theory, looks fancy, but in reality, I'm interested in points of interest, right? In observables and things like this. So what do I learn from that? Just to tell you a few things how it is used, right? So in model fidelity and model misspecification, P is the original model, Q is some approximation. People are trying to prove that this thing is small, and the size of the system, that's how things scale, I'm afraid. Lots of work on that by numerous people. And then there is another set of people, right? All this set of people, right? Some of them are in materials, and some of them are in actually computer science, right? Machine learning. And they say, well, instead of trying to build the guy who's close and test if it's close and prove something or whatever, maybe you should just go and have your favorite family of approximate models and minimize. And then, as we said, what happens to your observables, that's your problem now. But the idea in the let's say bidirectional inference is that I will replace this with that. So I won't do, so if P is a posterior, right, in a Bayesian approach, I can replace this with Q of theta. Instead of doing complicated MCMCs for P, I'll do them for Q. Right? And my life will become simpler. Also, there's some mileage to be gained by switching around P and Q. There's a great work by Tom Minka through the years on these types of methods, which are called expectation propagation methods. Right? But I won't get into this. For example, this review article must have thousands of citations. Right? Same thing with this one. It's a super active community, right? And also you can play with this software called STAN, right? Which is, you can play with that also with, you can actually implement variational inference for your favorite small problems. So let's go to sensitivity analysis, right? Let's pick one of these, right? And get into that a little bit more. So we will look at Langevin and we'll do stochastic dynamics like Langevin or kinetic Monte Carlo reaction networks. So more interested in this community maybe. We will have the usual issues. Now, one of the issues which I did not discuss earlier is the non-equilibrium issue, right? So many systems that I'm interested in are driven, right? So there is no steady state that is known. This is a typical example of a known steady state, which is called a Gibbs measure. So, for example, if you have a reaction network, you don't know usually the steady state unless you are in a trivial birth-death process, right? In the birth-death process, you know exactly what the steady state looks like, right? And there are a few others, right? Like maybe the Schlogel models, a few very special cases, right? But usually you don't know that.
Can I just be a pain in the rear for just 1 second? Ask a question. So when you, what I might call a non-equilibrium steady state, I can think of a non-equilibrium steady states that have the form Eta and Hamilton. It looks like a Gibbs measure.
Yes.
So it's for me, it's not about the measure; it's more about the dynamics.
It's
So, if I do globular
yes,
dynamics,
correct.
then it's a non-equilibrium steady state. But if I do
dynamics.
Hamiltonian dynamics,
The
it's
system
then
is-
it would be
The system is not reversible.
right. But that's what. But the measure could still look like that. If I do.
It will, yes, you're right.
Okay.
You're
All
right.
I just
You're
want to
right.
make sure
You're
I
right.
understood what you meant.
You're
Okay,
right.
fine. I'm good.
What I mean is a system that is intrinsically
Yeah.
non-reversible, so I cannot play any games of detailed balance
Okay.
and
Great.
construct stuff, right, with my own hands. Right? This will become clarified in a second, right? Yes. So, right. So sensitivity analysis is central, right? So this is one of my from an old, very forward-looking paper here, engineering paper from 2006. It's just a fantastic paper, right? So parameter sensitivity. I mean, you look at it and say, "Wow, these guys were good," right? So they have everything that we're talking about today, right? Many years later, right? Based on parameter estimation, experimental data collection, right? And the parameter sensitivity is central. So just some background and some other methods, right? So that maybe you've heard about some of these methods back in March, maybe, right? So if I have a stochastic system, right, I'm going to try to play this sort of the same game that I did before with ODs, kind of, right? So I can look at finite differences, right? So this is my observable, this is my probability, and I can look at things like that. There are methods that try to do this more carefully, on pathwise methods and Machiavellian calculus. Machiavellian calculus, as we said, doesn't scale. Pathwise derivatives have their own issues. They are a very intrusive method, so you have to get into the code, right, and get your hands in it. A great method by Peter Glynn. Peter Glynn is a very prominent operations research guy, member of the National Academy of Engineering. One of his main contributions is this method. It's a very simple method called likelihood ratio method. You want to find this derivative. I'm just paraphrasing here, right? You just take this derivative inside, differentiate your model P, but then you write P as you divide with P and you multiply with P. That's the derivative of the log, so that becomes an expected value. The whole thing becomes so this derivative becomes an expected value. Everything that's an expected value is an observable, so you can simulate it with your standard solver. So in other words, you can take your observable, you can augment it a little bit, right? And now you can use this as, with your standard solver, it's a non-intrusive method, right? This also looks very much like linear response methods. So it's called mechanics, lots of literature on that. Also lots of literature for discrete time systems in OR, right? One of the issues that this method has is that it, at long times, the variance scales linearly, so it's terrible. But it can be fixed. Now about finite differencing, just a few words about that. What we do here is that this is finite differencing. One of the things that I'm always worried about variance, right? So the variance of what I have in here is basically this with baby calculation. So that says that the more coupled you are, right? The more coupled you are, right? The bigger this covariance is, the smaller the variance is going to be. Here it is, right? Here's an example, right? Of a simulation of uncoupled, where this is 0, right? So you see the variance is getting very big, and this is where the variance is actually, this has been coupled in some mysterious way. And the variance here becomes much lower. So here, this is so there are methods that try to make this covariance non-zero. And the first such methods, well, not the first such methods. There were methods like that before in various communities, but at least for reaction networks, the first such methods were done by this paper, Raffingham, Shepard, Kamash, J.K. Fizz, common random number type of methods, but some more twists and turns. I think that a very important contribution has been done by David, where he built a joint Markov process for that, for well-mixed systems. This is a great way to think about these problems, and we've used this to do spatial dynamic modeling, spatial problems, where you have much more freedom and you can actually optimize the coupling, find an optimal coupling. And optimizing is such a great thing, right? So look at the variances here. For these spatial distributed problems, where you have high dimensional spaces, common random numbers that don't help you at all. You are dead, basically. Right? Your variance is huge, right? This is the coupling of the Anderson paper. It's much better, but optimized coupling is really give you very significant reductions in variance. So coupling is a great method also because it does not require absolute continuity. Right? So I will not pursue that here, but one of my postdocs is using it to do sensitivity for generalized Langevin. That is a very singular object. So this was work by my student Jonathan Apatzis. So these are great methods, but they have one issue, right? That they have to calculate gradients, right? So if you have a very high dimensional system, you have too many gradients, so it doesn't scale well. This method with a number of parameters. Now, a different approach to sensitivity analysis has been proposed in lots of different literatures, in civil engineering, but in computer science. But the two papers that I like the most are those two papers here. They are both PNAS articles from 10 and 11. One is by Andy Maida and one is his postdocs, and the other one is from a group at Imperial. It's on biochemical reaction networks, and they use linear noise approximation models. And their idea is to take the model, perturb it, and measure the loss of information, right? And that's going to be the metric for sensitivity. The more information you lose, the more sensitive you are. The less information you lose, the less sensitive you are, and that's that. And in both contexts, the problems had, the setups had a known distribution. I won't say gives them, no. In the linear noise approximation, it is not because Gaussian, right? As many of you know, right? You know this approximation. It's an approximation which is an approximation beyond the chemical Langevin, but before the big field, right? It lives exactly there, right? So, and Maida and Grescorian were doing maximetropy methods, so they knew the structure was of that type. And if you know your noise, if you know your model, you got to stick it in here, and good things happen. Right, here it is. The relative entropy looks exactly like this, so it's equal. It's equal. These are the partition functions, these are the normalizers, right? And if you want to understand this, if you want to minimize this, if you want to see which direction is more important, you can actually solve for that. You can take derivatives, and partition functions go away, and life becomes very streamlined. The problem is that in many of these dynamics problems that we're interested in, we don't know how the distribution looks like. Again, you know distributions, how they look like, if you're in a setup, in a simplified setup, right? Like Bernoulli processes, right? Or like some linear Langevin equation, or some Ornstein-Uhlenbeck process. But in general, we don't. So we had to go to path space, right? So we had to go. So path space is an attempt to do things for time series, for dynamic objects, also for non-equilibrium mechanics. Non-successful mechanics, it's known that if you want to look at non-equilibrium steady states, path space is the way to go. There's no other way. You don't cut corners. So things in path space look a little bit like this. I have a time series, right? I'm right here discretely, and I'm going to assume just for now that's Markovian, because life is simple there. And also, I'm going to assume it's a steady state because, again, every calculation is simple. If you want to look at the probability, if you want to know the probability of this particular time series, well, here it is. The probability of this time series is this one, at parameter theta. It is the probability of sigma 0 times all these guys because of the Markovian property. These are the transition probability. These are the transition probabilities. And if I have another time series that corresponds to another parameter theta plus epsilon, I can do the same. And then now I can go back to my relative entropy and stick them both in. So that would be relative entropy right here in path space, in the space of time series. So now I'm interested in data that have actually, which are correlated. They are not independent data. So I have to find a way to deal with this. And here's a simple calculation, right? If you have all this, so I just want to show maybe one simple calculation. If you take these formulas and you stick them in here, right? Take this, plug it in there. Take the same thing, plug it in there. What happens is that the special structure of relative entropy kicks in. So relative entropy, as we said, has a special structure. That's why it's special, right? You can see it here. So you have this over that, the logarithm, right? So So it's logarithm of a product, the product comes out, becomes the sum, goes all the way out, and then you can start integrating. You can integrate from the one end, right? If you integrate the very last point here, you get 1, and down here you can use the stationarity, and everything gets a very compact form, right? But the property of the logarithm must key here, right? So you get that this guy is t times h plus the relative entropy of the steady states. This object here, because it is basically, this object is a relative entropy per unit time, if you want, right? If I can divide with 1 over t here and send t to infinity, it will be relative entropy per unit time, so that's why it's called relative entropy rate, this object. This object, as t gets big, dominates that guy, right? Which are the steady states. So if I don't know the steady states, I can throw this away. I don't have to worry about this, right? That was back to your example question, so I can focus on that. Who is this guy? Here, let's take a look at this. It's right here, this relative entropy rate. It involves, in this baby case, right, of discrete time Markov chains, the one transition rate, the other transition rate, and this transition rate over here, right? So it involves only local dynamics, right? So usually local dynamics, usually you know that, right? Of course, there are problems where you don't know them, but in this context you do. And this is sampling with respect to the steady state. So if I want, if I take a look at this object is an observable, is it, right? So if I have an efficient Monte Carlo simulator that can take me all the way to the steady state, then I can sample this guy. Right? There are no partition functions, there are no objects of that.
So one good property that you used here is that if your random variables are like composed of independent subvariables, then the relative entropy sort of adds. Is that right?
That is the even more trivial version of this.
This is just the Markov property.
Yes. Here I'm just using the
the
next level up. Here I'm using what you just said, next level up, right? Markov property, right? Yes. If I have more memory terms, I can keep doing. Keep doing this, right? Keep doing this. I can keep playing this game, right? So, right. So yes, I guess we said all that, and there are statistical estimators. There's an even new statistical estimators by Manfred Opper's group in Berlin for rare that look very promising. So I guess I said it's an estimator, can be used for non-equilibrium problems, right? It's as a way to understand distance in non-equilibrium problems. It works in translinear regimes also, but I'm not showing the calculations. It works in problems with memory. And there is some very interesting follow-up work by different groups in Stanford and the University of Chicago, where they use spectral methods to calculate the rare, and also they use it as a maximum entropy tool. It's very promising. But we're not doing that. So, and another angle is, so some of you who are familiar with information theory, one of the concepts that you know there is the concept of Fisher information. So there is a Fisher information also for this in this context. So this is the rate that we defined earlier, right? Perturbed by epsilon. I can expand in epsilon if everything is nice and smooth. Not always the case. You'll see an example. And this object here, this matrix over here, looks exactly like this. So it's a Fisher information. It's the Fisher information matrix. It looks like the classical Fisher information that we all learn in statistics. Hopefully, we took a class on that. I didn't, but I will learn it later. So that's the classical Fisher information. However, it involves dynamics, right? So that's why it's called path space, right? So it involves dynamics, and it's a great guy. It's a great object in the sense that it's a matrix. And if you do spectral analysis on this matrix over here, right, you can understand which are the most sensitive directions and the least sensitive directions. Right? Diagonal values and diagonal vector analysis for this. Right? It has a sparse structure. We'll see that in the next slide. At least for reaction networks, it has a sparse structure. And the stochastic gradient free, right? So you don't have to do all these gradients that you do before, right? So this is just spectral analysis, and allows us to do very high dimensional problems and the standard sensitivity. And also there are some Cramer-Rao type theorems. Remember, the Cramer-Rao theorem, Fisher information, the classical Cramer-Rao is a fundamental quantity that bounds the values of estimators. Right? So we have similar concepts here, but not for dynamics. And a lot of this work can be from these earlier papers. For reaction networks, right? You'll see actually some chemical reaction networks, for which I know very little, so you can ask me anything. This FIM, right, this object here, has an amazing structure, right? It is block diagonal, and basically you see with each reaction how many parameters does it depend on, right? So this dependence is reflected here on the matrix. So that means that you don't have to calculate the whole FIM. The calculation is order. So you see, this is the number of parameters, right? So calculating this block diagonal guy scales with the number of parameters linearly, right? So that makes the scalable object. Well, that's a chemical reaction network of a model that I know very little about. Is a cancer-related protein. It's one of the many p53 models. One that has 3 variables here. You see that these models are stochastic, and also they are very non-Gaussian, right? Because they go all the way down to 0, right? In this particular parameter regime, which we took from this paper by Komorowski. So it's a model that's very non-Gaussian. It has to be stochastic, right? For that also, because it has very low populations. A much bigger, so this is a small problem, right? So I just want to show you, so it has just 7 parameters, right? So I don't want to show you that. A much bigger problem from an old paper. One of the great things in this community, right? In this community, this biological community, is that you have fantastic curated databases. So you can just go in there and grab models. You can see the discussion about them, parameters, and can just use them to test our numerical methods. So this is a model that has 207 parameters. This is a particular GFR model. I know that next week there is a talk on GFR. This is a well-mixed problem, but it has a huge number. It has a fairly big number of parameters, right? So for that, it's very easy to do sensitivity analysis with Fisher information. Well, you see the complex network is part of it. In reality, in the background, this is a continuous time jump Markov process. You can do the math for that. I just showed you the simplest case before. This is the case where you have jumps, total rate and transition rates and all that. We saw them yesterday in the talk. But that's the result. This is the result at steady states, at transient regimes, log scale parameters, right? Very few are sensitive. Most of them are insensitive, right? In this particular situation, sensitivity changes, right? In these regimes, these types of things have been also witnessed by James Sethna and his group at Cornell, where they have this concept of sloppiness about models that somehow you have too many parameters and most of them are insensitive and you shouldn't worry about them. So in some sense, this sort of takes this at the stochastic level and quantifies it. Also, we've done the same thing for Langevin dynamics. So in this not so complex molecule, but this is a sea of methanes, and these are the different interactions that they have: non-bonded interactions and bonded interactions. Who is the most important? One can do again the calculations here. This is the stochastic differential equation setup, right? The general basically setup with complex potentials. So the papers, relativism looks very interesting in this case. It turns out that it looks very much like this concept of force matching in coarse-graining that was introduced by Greg Voth maybe 10 years ago at the University of Chicago. So it's a way to maybe make these types of methods actually rigorous, right? Think of them as path space, making them methods which can handle non-equilibrium problems. So these are the results here, and you can calculate Fisher information and all that. So,
what are the capital F's again?
The capital F's, oh, it's the force. It's a force, right? It's a gradient of this guys.
And the reason that it pops out, just it involves the force, is because you have overdamped
I
dynamics.
can show you later.
Yeah.
Yes, I have at the very end of the talk, but I don't think I might get there. Yes, yes. So it's actually all these methods of force matching by both can be seen in that level, that regime, but actually they have corrections, and not what both said. They have corrections.
But Peter asked if you were using overdamped dynamics.
No, this is Langevin.
And does Q are path space probability measures, right?
Yep.
I guess what I was expecting is that the, oh, I see. Okay.
This is what you get, yeah. So you get the force.
I mean, you don't get any term for the inertial terms then? I would expect you have like P dot equals F and then X dot equals P.
You get the force. So relative entropy is force. That's the difference between, so relative entropy is potential. If you do this, right, you saw in the beginning, right, we have this relative entropy calculation for equilibrium objects, right? Where that will be the potential. Right? So there, relative entropy is actually potential plus some stuff. Rare is force. Remember, there is this different perspectives on whether you should be focusing on force or when you do coarse-graining, right? Or on the potential.
I guess that's what I'm wondering is, I mean, normally if you look at if you're looking at inertial dynamics, you have a kinetic energy component to your entropy in addition to the potential energy. And so the kinetic energy seems to play no role in your.
Just a force. So that confirms both methods. People did not understand why they work so well.
Markos, can I try to answer his question? I mean,
Yes.
since the forcing is, since the noise is directly in the force term only.
Oh, I see. So he's not
So
changing
what that
the
is
energy.
that's the infinitesimal variation in the force you have to
Right.
produce to compensate for the change in the drift.
Now you're talking persona.
It's Gersonic.
It's-
That's the infinitesimal action of Gersonic.
Remember, this is Gersonic. All these calculations are Gersonic, right? And that's why I said that these methods are good, but they have some limitations because of Gersonic.
So they don't mean absolute continuity, but they kind of do.
But I guess,
So this is Gersonic for Langevin. There's nothing magic about this. What's interesting that comes up in this relative entropy rate calculation. Oh, okay.
Infinitesimal large deviation action.
Yes, intimately related to that. Yes. In any case, all that is here, right? All that is here, right? In this last paper. I observe also on that. On both. Yeah, both. This is more coarse-graining, but yeah. So right. So okay, fine. So we talked about fast-paced methods, right? Fast-paced methods allow us to go for very long times and do sensitivity analysis. But there's one thing which I want to bring up. I don't think I have time to discuss it, but it's more of a math, stats, computer science type of question. It's okay. So you do all that, right? You focus on information metrics, right? Like all these communities. But what do you really learn? What do you really learn about your statistical estimators? Right? About your observables? Do you have any guarantees of performance? Right? And some of the usual issues, right? So this is the next question, right? So what do you learn from information theory about observables and quantities of interest? And one would say, well, I know a great inequality that does the job, right? It's the Pinsker inequality, right? And that's my observable, and that's how it looks like, right? If you control the relative entropy, you control your observables, great. Right? That's exactly what you should be doing relative entropy minimization, right? Or sensitivity analysis. Well, yeah, fine. But remember, systems scale with n, right? They can go at long times. So do such an inequality scale with n or long times, right? That's so in the end, is KL the right metric, right? And what would be even more? What would be the right inequality here? Right? Well, this is not the one. So there are different metrics. One of them is missing, reason, because that work isn't published. So, so I don't have that missing Wasserstein guy there. So there are different types of metrics between the distributions. Some of them are divergences, some of them are distances. This is Hellinger, this is chi-squared. And I want to see what I learn about my favorite observables in the most elementary environment, right? Which is always IID, right? Independent identical distributed. Also, it's the environment that a lot of statistics are done, right? So I have n independent samples from two different models. And I want to look at the distance between those two models here, right? And I want to control different types of observables, like sample mean, sample variance. In other words, I want to control expected values of these types of objects by the relativity. Okay, I have 5 minutes. So I have a title here, post-scaling properties, right? So nothing good is going to be in this slide, right? Yeah, there's nothing good in the slides, right? Okay, so I'm going to take this example. I'm going to take relative entropy, right? And each one of this so I picked 3 inequalities. We've tested all the inequalities that we knew, and even some that were suggested by Andrew Stewart. And before we tested them, we improved them also, and still they failed, right? So you take this previous IID examples, you stick them in here. This guy scales like n. This guy is L infinity, does whatever stays bounded. N goes to infinity, this goes to infinity. This bound, from this bound you learn nothing, right? The bound goes to infinity, doesn't inform anything about this. If this is small, that's small, something like this, right? You don't learn anything of that type. Hellinger bounds, also there's some bounds that Andrew Stewart has done with L2 norms here, right, in a very recent preprint. That also can be slightly improved. This is the Hellinger distance. You stick in this IID example, this guy here goes to 2 as an equation, right? So this bound is bounded by some trivial bound, which is actually 2, right? So 2 times the absolute, the infinite norm. So again, it's a non-discriminating method. Does not discriminate the models. This guy with that guy. And the one that seemed more promising is, you see, the scaling was bad, right? So so I had an n here, and this guy's right square root of n, and this guy here was constant, so we could not kill that guy. So there's something that seemed more promising is the Chapman-Robbins bound. So it's a generalization of the Kramer-Rao bound. It's a more general version. It's a very important bound statistics. And you replace this guy with the variance. You say, okay, this is fantastic, right? This is great because look at the variance. The variance scales like 1 over n, right? And you may kill that guy over here at the end, right? So this guy looks good. Unfortunately, chi-squared is terrible, right? It scales exponentially as n goes to infinity. So none of these inequalities are good, right? So for the book that I'm interested in, none of this deformation inequalities work, right? They cannot be. So I can do all the variation inference that I want. I can do all the machine learning that I want. I learn nothing.
Sir, can you remind me PM, what's the definition?
PN was, in this baby case, was just a
Oh, sorry.
product.
All right, sorry.
The best actual example, I'm not showing it, which is in the paper, is when this is a Markov chain. It's a Markov chain. But yes, but this is the simplest one to show. Right. So basically, there is a new inequality, right, that we proved with Paul Dupuy and Plechach and Yanis Apostol, this in this paper. There is a new inequality that has this weird new objects, psi, we call them. We call them goal-related divergences. Basically, they are divergences themselves, these objects, because they are zero if only if p is equal to q, or if f is deterministic. So they are sharp in that sense. If you linear if p and q are close, they look exactly like this. Look exactly like this, right? So we can prove that. And in fact, in this recent preprint, which you can find online, we actually have proved that this bound scale, right?
Aren't
So
you
they,
concerned-
they resolve all these issues that we saw earlier.
aren't you concerned someone's gonna turn your goal-oriented divergence into a god?
Into a what?
It's like an acronym.
Oh, yes, right, we thought about that, but it was too late. It was too late, it had been, yes. So someone pointed this out, yes, yeah, right, yes. I mean,
We have
it was,
a gun on our
it was too late for this paper, but we don't use it here. Yes, so yes, I'm very skeptical about this type of methods. There are many, but not ours. We're not in that business.
Yeah, but that's a solution to a PD, right? That's a solution to a certain, that's a variational solution to, that's the moment generating function and the,
You'll see the second.
okay.
So why does it work? Why does it work, right? Let's go back to this example, that silly example that I showed you with this IID, right? It works because, I'm looking at the linearized case, I mean, the moment generating functions are fantastic tools, and we saw them also yesterday in action. The value scale is like 1 over n, the leading term scale is like n. This guy kills that guy, everything looks good. Bound looks good, right? It fixes all the previous problems. Also, if you look at this bound for Markov chains, you can compare Markov chains at long times, right? That would be certainly of interest to Jonathan. He's been thinking about these problems. Long time errors. So actually, relativity rate pops up mysteriously, right? Pops up here. These are ergodic averages, basically. And also this guy pops up, which is actually the integrated autocorrelation function. People know this when they do Markov chain Monte Carlo. It's an important quantity is also statistical mechanics. Molecular stat-mech describes, how processes decorrelate. And Jonathan's question, he asked me, how do those things pop up? They pop up in a very simple way from here. Right? From this guy. Right? So I'll wrap up. Yes. So from this guy, right? So it's a very trivial bound. It's a very, very trivial bound. Also here, when you look at that, you see actually that this is are robust, right? Robust in the robust optimization sense, in the H infinity control sense. Right? So this object here is my model specification, if you want, how far away P is from Q. So it's related to that object, and the bounds become sharp in that sense, right? So if you restrict yourselves into these types of models, then my bounds become sharp. Also, there is some very interesting related work, not on inequalities, but on this type of model, on decision making under uncertainty using information theory, by two guys, that each one of them has his own Nobel Prize. Sargent and Hansen, there's this great book on robustness that is using these types of metrics to assess model specification in macroeconomics. Also a great paper by Paul Glasserman on some related issues in finance. Well, we can use them. Let me skip this example, which are about nonlinear response, right, and how to do nonlinear response. Let me go to the very end here, right? Here's a way to do a very fast sensitivity analysis for complex, high-dimensional, fairly high-dimensional reaction networks. Here's an example that we picked up from this wonderful database, curated database, right from here, United Kingdom. We had a model with quite a few parameters and species, not that many, but we just wanted to do a demonstration how we can use these upper bounds. So these upper bounds, basically, we can use them. So these upper bounds imply this type of inequalities you see over here, which is on the sensitivities. We saw that autocorrelation, Fisher information. Fisher information is very easy to calculate. Autocorrelation, you must calculate it always, right? Because if you want to give confidence intervals to your calculations, it's part of your calculation anyhow. So if this is small, sensitivity is small, so you don't forget about it, right? So here what you see in this picture is parameters and observables. And they are arranged according to how big these bounds are, right? So these bounds tell you that in big part of this parameter observable domain, things are insensitive, so you shouldn't worry about them. And wherever this thing gets big, well, then maybe you should go there and do David Anderson's methods. If you didn't do this screening, right, screening based on these bounds, things would look like this, so you have to go through each and every case. In this case, there are 1,150 sensitivities. Well, there are much fewer left here to deal with. Okay, I'm skipping the events, and I'm skipping conclusions. I just want to thank my collaborators and students and postdocs. In particular, this work that I present is work with Paul Dupuy, Luc Ray-Bellet, my former student, George Rambazis, my former postdoc who jumped into the dark pool of Greece this year, doing bio, and my current student, G1. So I'll stop here. Thank you.
Let me see if I'm trying to understand your motivation for these improved bounds. So I think what you're seeing, if I understand what you're seeing, the problem is if I have somehow, imagine I just have a simple process where I just add some IAD noise at every time increment, but maybe, for two paths I use the same model, and for another two paths I use a different model for the noise. And you're saying is that as I run the thing longer and longer and take more time steps, and I calculate the path space, the relative entropy between the path, that's going to get bad as n goes to infinity, so I can't tell the difference between two paths generated by the same noise model or a different one.
Yes. It doesn't be on path space. It could be for any high-dimensional distribution.
I'm just trying to get a specific example.
Any high-dimensional. So take, for example, the Gibbs measure.
Yeah.
Right? You can't say anything.
As you put more and more independent
Yes.
or Markov
Yes,
dimensions.
so that's the example which I skipped, right?
Yeah, so
So I'm saying the Gibbs measure because it's the simplest example, which is not IID, but it's high dimensional, has no dynamics, right? So if I have a model, so this is a phase diagram, right? This is a phase diagram, right? In particular through phase transitions, not alone, right? And you can see actually where your actual model is, right? You cannot get any bounds. So this is true non-linear response bounds. Perturbations are very big. You're not anymore sensitivity regime. But if you don't have the right bounds that scale right with n and with t, you cannot go to the thermodynamic.
but you're saying, I would have thought.
So this is a thermodynamic limit calculation, right? Any type of phase diagram is a thermodynamic limit calculation. So you cannot do that.
I would have thought that this was just a property of relative entropy, but what you're saying is it's not a property of relative entropy. It's kind of how the bounds you're using deteriorate this limit.
Yes. You need robust bounds. And the other bounds are not robust.
For increasing dimensionality.
Yes. For high dimensional problems. It matters what you do. Yes. It matters that, yes. So that's why you need to keep this high dimensionality in mind when you try to do variation. Same thing when you do variational inference, right? Machine learning and variational inference are touted as the next solution to everything, right? Well, if you go to a high dimensional problem, what do you learn from that? That's the question.
So I'll take up their cause and fight back a little. I mean, but
Yes.
all of your high dimensional models and all of your lessons
Yes.
you learned by those
Yes.
various bounds were always product measured. I mean, that's what your exam, your statements there, right? So you're really saying,
Not always.
but the ones you showed, I mean,
Yes.
and the
Well, the Gibbs measure is not a
the
problem.
unassailable product measure. I mean, even if you look at like the
The-
models
the-
like
the-
Andrew
yes,
does, I mean,
yes,
they're
yes.
all dominated by a product measure. So I mean, that's really a statement about there is no low dimensional structure in the high dimensional space, where a lot of the people who are doing machine learning are always wanting to look at systems that, morally speaking, have a low dimensional representation, but that low dimensional representation is hidden. And
Yeah,
that's
right.
that's an orthogonal setting from what you're talking about.
Well,
Or do you disagree with that?
I disagree with that.
Fight back.
Right.
I set you up a straw man.
Yes, no. Look, I mean, it depends depends on the problems that people are looking at.
Yeah.
If you look at this, at the typical variational inference setup, you don't know that there is a hidden manifold or something like that. You have, it's a classical Bayesian problem that you want to approximate to something. What I'm saying is that as this problem goes to higher dimensions, then I don't know what you learn from this. That's my only statement.
But if somehow you're adapting to the low-dimensional structure in it, you may learn a lot, actually, as it goes to higher and higher.
Ah, yes, correct, yes. If you, so what that means is that basically you have to find a way to sort of keep your dimension fixed.
Yes, correct, agreed.
Whatever you do, right? Because if you don't do that, well, I don't know. And of course, there are many problems which are genuinely infinite dimensional, right?
Right.
Like this paper problems.
Right, but then they're infinite dimensional, but then they're morally product structures.
Yes,
And
morally.
that's a
Yes.
different,
Yes.
that's a different.
Correct, yes. But the diffusion is not really a product structure, right? It has correlations. Well, depends. Depends on the problem. Now, one issue with this, right? Let me say one issue with that, right? One issue that's actually we are working on, and I did not mention because I didn't talk about relevance, is that this bounds. Yeah, these
Yeah.
guys. These guys could be very nasty guys, right? So some of the, right, in some cases you can calculate them or you can bound them, or if you do small perturbations, things are very good and work very well with the small perturbations I showed you. But in general, this is what we call a risk-sensitive functional. So to be able to have the risk-sensitive functional, you may need a rare event sampler. So that means that if you want to go from model P to model Q, where Q is far away, you have to pay a big price. And that's the price. So we're using some of Paul's infinite swapping algorithms actually to explore these types of things.
Okay, thanks.